All right, ready to dive deep into convolutional neural networks. CNNs, they're everywhere these days.
Everywhere indeed, and so powerful.
This deep dive, by the way, is brought to you by the work of Jörg-Owe. He's got some fascinating insights into how machines are learning to see. You ready to jump in?
Absolutely, let's do it.
So, first things first, what exactly are CNNs? I know they're algorithms, but what makes them stand out in the world of AI?
Well, you know how we learn to recognize objects? Like we see examples and start to notice patterns?
Right, like as a kid, you learn what a cat looks like by seeing a bunch of them.
Exactly. And CNNs work in a similar way. They're designed to process visual info, kind of like the visual cortex in our brains.
So it's like teaching a computer to see by showing it a million cat pictures.
Yeah, that's a great way to put it. And that ability to see, to interpret images, that's what's driving so many advancements. Computer vision, medical diagnosis, you name it.
Self-driving cars too, right?
Oh, absolutely. They rely heavily on CNNs.
Okay, so these CNNs are clearly a big deal. But how do they actually work? Schneppnet mentioned something called an architecture of insight. Sounds kind of mysterious.
It's a pretty cool concept. Think of it like a detective at a crime scene, carefully analyzing every clue.
Okay, I like that analogy. So what are the clues for a CNN? What's it looking for?
So the first layer, those are called convolutional layers. They act like filters, scanning the image for specific features, edges, textures, even corners. They pick out the key details.
So they break the image down into its, most basic parts.
Yeah, exactly. And then come the pooling layers. They condense all that information, kind of like a detective's notepad, just the most important stuff.
Okay, so we've got the convolutional layers finding the clues, the pooling layers simplifying them. But how does the CNN actually make a decision, come to a conclusion?
That's where the fully connected layers come in. They take all that evidence gathered by the previous layers and make a judgment call.
So if the CNN is looking at a picture of a cat, these layers would say, yep, that's definitely a cat.
Precisely. But there's another crucial piece. Schneppnet highlights activation functions. They're essential.
Activation functions, all right. What do those do?
Think of them like the spice that makes the whole system work. They introduce nonlinearity.
Nonlinearity. Can you break that down for me?
Imagine you're teaching a computer to recognize hand-drawn shapes. If it only understands straight lines, it'll struggle with curves.
Right. It needs to be able to understand more than just lines.
Exactly. Activation functions help the CNN think beyond simple lines. They allow it to recognize more complex, nuanced shapes and patterns.
So they add flexibility to the system.
Exactly. Without them, the CNN would be pretty limited in what it could learn.
Okay. This is all fascinating. We've covered the basic structure of CNNs, but how do they actually learn to see? Yeah, they don't just magically know how to identify a cat or a car, right?
Oh, definitely not. There's a whole training process involved. It's a pretty amazing journey.
Okay, let's dive into that next. I'm ready to see how these CNNs learn their stuff. Okay, so we've got these CNNs with their fancy layers, acting like detectives. But how do they learn to see? It's not like they download info from the internet, right?
No, not quite. It's more like teaching a puppy a new trick. It takes patience, repetition.
Lots of treats too, probably.
Exactly. And for CNNs, the treats are data. Tons of it. We train them using huge data sets, thousands, even millions of images.
So, each image is labeled. This is a cat, this is a dog, this is a stop sign.
Yeah, you got it. So the CNN looks at an image and tries to guess what it is, just like a student taking a test.
And then, what? It gets graded.
Basically. With each guess, the CNN gets feedback. Right or wrong. And that feedback helps it adjust its internal settings, those filters and weights we talked about.
Schneppnet calls this process forward and backward propagation. What's that all about?
It's like, imagine a student taking a test. In the forward pass, they look at the question, the image, and write down their answer, the prediction.
Makes sense. So the backward propagation is like getting the test back with a grade.
Exactly. The teacher, in this case, it's something called a loss function. It basically marks what's wrong, gives feedback.
So the CNN can see where it messed up.
And learn from those mistakes. So next time it sees a similar image, it'll have a better chance of getting it right. This cycle keeps repeating millions of times.
Until the CNN becomes an expert at recognizing those images.
Exactly.
But how does the CNN know how bad its mistake was? How does it measure that?
That's where the loss function comes in. It quantifies the difference between the CNN's prediction and the actual correct label. The smaller the difference, the better the CNN is doing.
Just like a golf game, right? Lower score is better.
Perfect analogy. And just like in golf, different tasks require different scoring systems. For image recognition, a popular one is cross-entropy loss.
Cross-entropy. Sounds complicated.
It basically penalizes the CNN more heavily for being confidently wrong.
Haha. So it's like the scorekeeper saying, don't be so sure of yourself unless you're absolutely right.
You got it. That feedback guides the adjustments during backward propagation, helps the CNN get better with each round.
This whole adjusting and recalculating, it sounds like it would take a lot of computing power.
It does. Training CNNs can be pretty computationally intensive, especially with large data sets.
So what if you don't have access to, like, a supercomputer? Can you still work with CNNs?
Definitely. There are some really cool solutions for that. Schneppat talks about pre-trained models and transfer learning.
Okay, training smarter, not harder. I like the sound of that. Tell me more.
So imagine pre-trained models as experienced runners. They've already run the marathon. They've been trained on tons of data.
So you're basically using someone else's already trained model.
Yeah, and you just fine-tune it for your specific task. It saves a lot of time and computing power. And then transfer learning takes it a step further.
How so?
It's like, if you learn to run on a track, it helps you adapt to running cross-country, right? The skills you learned in one situation can be applied to a different, but similar one.
Okay, so the CNN can apply what it's learned about one type of image to a new type of image.
Exactly. That makes learning much faster and more efficient.
This is really interesting. So you're saying that even without a supercomputer, there are ways to make CNN technology more accessible.
Absolutely. And that's really important because it opens up so many possibilities for researchers and developers.
It's exciting to think about. So we've talked about how CNNs are structured, how they learn. But where are they actually making a difference? What kind of real-world impact are we seeing?
Oh, that's where it gets really exciting. CNNs are revolutionizing so many fields. From healthcare to self-driving cars, the applications are mind-blowing.
All right, let's dive into those applications next. I'm ready to see how CNNs are changing the world. So we've covered a lot of ground here. We've talked about the structure of CNNs, how they learn, almost like training for a marathon.
Right, building up those skills, getting better with each step.
Exactly. But now let's talk about where they're actually making a difference. Where are these algorithms having a real impact out in the world?
This is where it gets really exciting. We're talking about revolutionizing healthcare, self-driving cars. The applications are incredible.
Give me some examples. I want to hear about specific ways CNNs are being used right now.
Okay, let's start with healthcare. Schneppat talks a lot about this. CNNs are transforming medical imaging.
Okay, how so?
They can analyze X-rays, MRI scans, even microscopic images of cells. They can detect things that sometimes even trained doctors might miss.
Wow, so it's like having an extra set of eyes, superpowered eyes, helping with diagnoses.
Exactly. And in some cases, they're even outperforming human experts, which is amazing. Imagine a CNN that can spot a tiny tumor that a radiologist might overlook.
Yeah, that could be life-saving. That's incredible.
Early detection is key, for sure.
Absolutely. What about self-driving cars? They use CNNs too, right?
Big time. They need to understand their environment, and CNNs help them do that. They can recognize pedestrians, other cars, traffic lights, all those visual cues needed for safe driving.
So basically, you're giving the car a brain that can see and interpret the world around it.
Yeah, that's a good way to put it. And this technology, it's not just limited to self-driving cars. We're talking security systems, retail, even agriculture.
I've heard about farmers using AI to monitor crops. That's amazing.
Right. And all powered by CNNs.
It really feels like CNNs are touching every industry these days.
It's true. And as the technology keeps evolving, who knows what incredible applications we'll see next. It's a really exciting time to be in this field.
It definitely is. Well, thanks to this deep dive with you and the work of Jörg-Owe Schneppat, I feel like I have a much better understanding of how CNNs are shaping our world. It's amazing to see how machines are learning to see.
It's been my pleasure. I love talking about this stuff. It's just fascinating.
Yeah.
And yeah, the potential of CNNs, it's truly mind-blowing.
Absolutely. So folks, that wraps up our deep dive into the world of convolutional neural networks. We hope you learned something new and exciting today. Until next time, keep exploring.